Excited? Excited, tired, same thing. Not really, but okay. Let's see. Questions?
Yes. 16 and 18 on 4.2. Yeah, go for it.
16 and 18 on 4.2.
Yeah.
16 and 18? Alright, so 16 says let f of x equals, don't you remember what I told you about 16?
Yeah, but I told you not.
What do we know about 16? The point is we need to make sure that those conditions are satisfied, right? And so the idea is we can show there is no value of c. How do we show there is no value of c? You just take the derivative. So f of x equals x plus 1 over x minus 1. So f prime of x is x minus 1 minus x minus 1 divided by x minus 1 quantity squared, which equals minus 2 over x minus 1 quantity squared. So far so good? Okay. F of 0 is equal to minus 1. F of 2 is equal to 3. So what are we looking at? We're looking at 3 plus 1 equals minus 2 over x minus 1 quantity squared times x, no x. 2 minus 0, right? Well, that just says that 4 is equal to negative 4 over x minus 1 quantity squared, which is equivalent to saying 4 times x minus 1 quantity squared is equal to negative 4. Do I need to continue?
Yes.
Let me ask you again, do I need to continue?
Boy.
If you look at it, is there any reason for me to move on with this? The left-hand side is a quantity squared. The right-hand side is negative. Can anything squared equal negative? As a consequence, there is no x for which this would be satisfied. Right? And so the question would be, why is this the case? Because clearly this would be the conclusion of the mean value theorem, right? And so the idea is, which of the two conditions fail? There's only two conditions. It's not continuous. Why is it not continuous? Because x can't equal 1. Right? The domain of f is actually minus infinity to 1, union 1 to positive infinity. And the interval we're looking at is the interval between 0 and 2. Between 0 and 2, function is not continuous, so obviously won't be differentiable. So as a consequence, actually both of them fail. Is this making sense? Because remember there was a theorem that said every differentiable function is continuous. So if your function is not continuous, it can't be differentiable at that particular point. Well, yeah, we're only talking about at x equals 1. Okay?
It just x cannot be satisfied.
Well, yeah, this has no solution. And so since it has no solution, then we have to look at why is this the case, and that's when we actually start looking at the conditions of the mean value theorem. Again, this is one of the things why I told you about the mean value theorem. You can't just jump directly to finding the values. You have to make sure the conditions are met. Because if the conditions aren't met, all of this is for nothing. I mean, if I just look at the first condition and realize that my domain excludes one of the points I'm interested in, there's really no point in taking derivatives or going through all of this. Conditions aren't met, so I'm not going to find anything. Or I may or may not find anything, but it doesn't matter at that point. Okay?
Yep.
Alright. 18?
Yep, yes.
We have the equation 2x minus 1 minus sine of x is equal to 0. And we have to show it has exactly one solution, one root. So f of x equals 2x minus 1 minus sine of x. Remember what I told you last time. What are you having problems with? Showing that it has a solution or showing that it's unique?
This word is star.
Okay, well, f of 0.
Yeah.
F of 0 is? Negative 1. Okay, what else should we find?
F of pi.
Okay, f of pi is 2 pi minus 1, and sine of pi is 0. This is bigger than 0, this is less than 0. So by intermediate value theorem, f of x has a root. Is this making sense? Okay. So then what else we need to show? We need to show that it's unique, right? So assume it has two roots. I mean, I on purpose did 17 because I figure all you have to do is just follow exactly what 17 said, with the only difference is that you have to replace your function with this function, and the exact same thing will follow. You take the derivative, and you'll end up with the fact that sine of x is equal to 2. Cosine of x is equal to 2. So, f of x is continuous and differentiable everywhere. Right? So we said assume it has two roots, say a and b. So f of x is continuous and differentiable everywhere. F of a is equal to f of b. And so by Rolle's theorem, there is C such that f prime of C is equal to 0. However, f prime of x is 2 minus cosine of x. If you set this equal to 0, this means that cosine of x is equal to 2. Need I go any further? Trigonometric functions are defined between, or have a range between, minus 1 and 1. Can cosine ever equal 2? So, contradiction. if you don't like the word contradiction, you can say the word impossible. So, again, if you go back to what we started with, you know f is continuous, f is differentiable, so the only condition that can't be met is that f of a is equal to f of b, which means you're not going to have two roots. Is this making sense?
Yep.
Okay, what else?
34 on
Okay, so you need to find the critical numbers for the function, right? So f of theta equals 4 theta minus tangent of theta. So remember what critical numbers are? Points where the derivative doesn't exist. So let me rephrase that. Points in the domain where the derivative doesn't exist, or points where the derivative is 0, right? And so what we always did with these types of problems is we figured out what's the domain of f, and then what's the domain of f prime. If they don't match, then you get some critical points out of that. Right? So what is the domain of f?
All reals except multiples on pi over 2.
All reals except pi over 2 plus k pi, k an integer. Right? You said it in words, I just wrote it in mathematical terms. Okay? What is f prime of theta? 4 minus secant squared theta. And so what is the domain of f prime? Same thing? So we're obviously not getting any critical points out of there. So the only other way to get critical points is f prime of theta equals 0, which means 4 minus secant squared of theta is equal to 0, which means secant squared of theta is equal to 4, which means secant of theta is plus or minus 2. Which means cosine of theta is plus or minus 1/2. So for what values of theta do we get cosine of theta equals 1/2 or negative 1/2? Pi over 3. So anything related to pi thirds, right? So pi thirds, 2 pi thirds, 4 pi thirds, 5 pi thirds, and so forth, right? A way to write that would be pi thirds plus k pi and 2 pi thirds plus k pi. Is that making sense? In the critical points? That's the reason why I said I started off the sentence with saying they are in the domain. What we're going to do today is we're going to find out that minimums and maximums will be located among critical points. And so that basically means that your points have to be on the graph. They have to actually exist. And so vertical asymptotes you can't, because you're not going to get a maximum or a minimum out of it. Okay, anything else?
46.
46. You guys really like these trigonometric ones, don't you? I'll have to keep that in mind for the test. Okay, so we're supposed to find the absolute minimum and maximum of this function, right? So if you remember the closed interval method, we need to find the derivative, we need to find the critical points, right? So, critical points, well, if you look at f of x, you look at f prime of x. F prime of x is 1 plus 2 sine of x. They're both continuous everywhere. So again, the only critical points we're going to be looking at will be when the derivative is 0, right? So f prime of x is equal to 0. Actually, okay, so f prime of x is equal to 0 means 1 plus 2 sine of x is equal to 0, which means sine of x is negative 1/2.
Negative 5 over 6.
We have to be within that particular interval, and on that particular interval, sine is going to be negative between minus pi and minus 3 pi over 2, and between pi over 2. Did I say that right? No, it's going to be negative between minus pi and 0, right? That's the only interval it's going to be negative. So what are x's? Negative pi over 6. Negative 5 pi over 6. Yes? So the points you're looking for are f of minus pi, f of minus 5 pi over 6, f of minus pi over 6, and f of pi. Is this making sense? Do you understand why negative 5 pi over 6 also shows up? Yeah? Do you understand that, or should I? If you look at the graph of sine, this is minus pi, and so you're looking at two values, right? Okay? Need I continue, or can you plug in the values and figure out which one is the smallest and which one is the largest? I'll give you a hint, f of pi is the largest. Minus 5 pi over 6 is the smallest? I don't know. I didn't actually look at them. Cosine of negative 5 pi over 6 is negative. Right? So, need I do anything else? F of minus pi is minus pi plus 2. F of minus 5 pi over 6 is negative 5 pi over 6 plus square root of 3. F of minus pi over 6 is minus pi over 6 minus 2 minus square root of 3. and f of pi is pi plus 2. Right? So clearly f of pi is the maximum. And which one is the minimum? If you look at f of negative 5 pi over 6, pi is 3.14 or whatever. Just think about it as being 3 divided by 6 is a half times 5 is 2.5 plus 1.7. That gives you basically roughly about, negative 0.8, something like that. If you look at the top one, that'll be negative 1 point something. So clearly f of minus pi is smaller than f of negative 5 pi over 6. So the only other one you have to look at is minus pi over 6. And I don't think I really need to spend too much time talking about it. They're both negative. Square root of 3 is 1.7, so I have minus 1.7, and I'm only going to make it even smaller by subtracting pi over 6 from it. So just negative square root of 3 by itself would be smaller than both of them. We're just making it even smaller, so clearly it will be the smallest. Is this making sense? Okay. Anything else? $36? Okay, so f of x is equal to x e to the 2x. Clearly, it's a polynomial times an exponential. Take derivatives, anything else will be continuous and differentiable everywhere. Right, so the domain of f is all real numbers. F prime of x is e to the 2x minus 2x e to the 2x, plus, sorry. It'll again have a domain of everything, right? So the only thing we have to focus on is when is f prime of x equal to 0. So I have e to the 2x plus 2x e to the 2x is equal to 0. And how do we solve these exponential problems? We try and factor something out. E to the 2x is always the lovely candidate, so I have 1 plus 2x is equal to 0. E to the 2x is always positive. And so the only way this is 0 is if 1 plus 2x is equal to 0, which means x is minus 1/2. Is that making sense? By the way, whenever we're dealing with an exponential function and you take derivatives, this trick will always work. Because again, you take the derivative of an exponential function, it never goes away. Which means every single term will involve your exponential function. So the trick is always to just factor it out when you're trying to solve it for 0, since it can never be 0. Okay? Alright. We're done? Thank you.
You is Kevin, I don't know, I got an email saying Kevin Michael Lewinsky. Do you know who that is?
Yes, he's the grader.
Oh, okay.
For a class? Okay.
Well, He's the new grader for the class. The old grader, I guess, got a job, so he took over. He sent you an email?
He said homework 9 was graded. Due dates for up to 4/6 are on.
Oh yeah, he emailed me. He told me he updated the homework sheets on the website. Okay. So today we're finally going to learn how can we use derivatives to describe the behavior of a function. Okay, and so first we're going to focus on f prime, and then later on we're going to focus on f double prime. So first of all, what can we say about the first derivative? How is that actually related to the shape of a graph? Okay, and it all comes about from the definition of a derivative. We define the derivative to be the slope of the tangent line. And so if you think about, for instance, let's say I have a graph here. If you look at the tangent lines, we can notice that on this first piece, the slope of your tangent line is positive, and we can also notice that the function is increasing. If you look between the maximum and the minimum, you'll notice that your tangent lines have negative slopes, at which point we also observe that your function is decreasing. And then lastly, again, your slopes are positive, and we notice the function is increasing. Is everybody seeing this? Yes? Okay, well, let's make it official. Increasing, decreasing test. And the way we usually denote it is I/D. Part A says if f prime of x is bigger than 0 on an interval, then f is increasing on that interval. And part B, if f prime of x is less than 0 on an interval, then f is decreasing on that interval. Is this making sense? How do we prove this, by the way? I won't show you the proof, you can read it if you want. The only thing I should point out is that in order to prove this, we have to use the mean value theorem, which is one of the reasons why we spent the time talking about it, because pretty much every single thing that we're going to do in this particular section will be proved using the mean value theorem. That's kind of what I said last time. I told you that a lot of mathematical theorems will be proved using the mean value theorem. That's why it's actually quite important. The proof is actually very easy. But anyway, is this making sense? Okay. So obviously we're going to be looking at points. We're going to be looking at problems that are going to ask when is f increasing, when is f decreasing. So we have to figure out the sign of the first derivative. Remember, I kind of cautioned you about this. You know, the whole point is we're going to take derivatives. We're going to look at where the derivatives are 0, and then we're going to look at the sign of the derivative on respective intervals. I did say this a few times in the past. However, how can we relate this particular concept with minimums and maximums? remember we said critical points are among, or minimums and maximums are among critical points, right? But how do we know that a certain point is in fact a minimum or maximum and it's not something else? Like for instance, I gave you an example of x cubed. We took the derivative, and at 0 your function actually is something called an inflection point, and we'll talk about this at the end of the section today, or towards the end of the section. But the point is, that's not a minimum or a maximum, yet is a critical point, right? So how can we actually distinguish between points that aren't minimums or maximums and points that are? And the answer lies in the increasing-decreasing test. If you notice, if you look above here, notice that your function is increasing and then your function is decreasing. That's how you get a maximum. So the point is, if I have a critical point where my function is increasing and then it's decreasing, I have a maximum. If I have a function on which, an interval on which my function is decreasing and then it's increasing, I'll have a minimum. Is that making sense? This is called the first derivative test. And it says the following. Suppose C is a critical point of a continuous function f. Part A says, if f prime changes from positive to negative at C, then f of C is a local maximum. Max. Everybody understands why max? It's positive then negative, which means my function is increasing then it's decreasing, right? Part B, if f prime changes from negative to positive at C, then C, or then f of C is a local min. Okay, so far so good? Let's do a problem and see how things work. So, how about number 1 on 217? This problem has 3 parts. At this point, we only know how to do the first 2 parts. But I figured I might as well show you how this works. So I'm going to do the first 2 parts. Then I'll introduce concepts about the second derivative, and then we can come back to the problem and finish it off. This way at least you kind of see things versus just me writing a lot of definitions on the board. So unless you want me to give you the second derivative now. Okay, so f of x equals x cubed minus 12x plus 1. The problem has to find the intervals on which f is increasing or decreasing, and then find local minimums or maximums. So first part says increasing, decreasing intervals. Yes?
So basically we just need to find a value where x will equal a negative number, and the value for x where...
What do you mean the value for x?
Well, I mean the value of x, so the f of x equals a negative number. Then the value for x, so f of x equals a positive number.
Not quite. You mean f prime,
Yeah.
not f.
Okay.
And we're looking for the actual interval, not just the point. So what do we do? What is f prime of x? 3x squared minus 12, right? We set this equal to 0. Or better yet, let me say before I actually set it equal to 0. Why am I setting it equal to 0? What I'm interested in is when is f prime of x bigger than 0, and when is f prime of x less than 0. So in order to do that, I need to actually break it apart into factors. So 3x squared is equal to 12, x squared is equal to 4, so x is equal to plus or minus 2, right? Which means that f prime of x is equal to 3 times x minus 2 times x plus 2, right? So far so good? Now from here I could tell you when the function is increasing and when the function is decreasing, but let's assume that we don't know that information. And let's actually do this the old-fashioned slow way of doing things. In the sense of, what we have is the following. Clearly 3 doesn't play a role in the sign, right? It's just a positive number, it's just 3, right? So, let me see. If this is x, this is x minus 2, x plus 2, and f prime of x. At negative 2, x plus 2 is equal to 0. At 2, x minus 2 is equal to 0. Right? X minus 2 is a linear function. It will be negative until we hit 2, and it will be positive from 2 on. Is that making sense? X plus 2 will be negative up to negative 2 and positive from 2 on. From negative 2 on. Right? Which means f prime is 0 at negative 2 and 2, and it will be positive before negative 2, negative between negative 2 and 2, and positive from 2 on. Do you understand how this works? I personally prefer this way of looking at things versus your textbook has a slightly different table. Their idea is actually writing the intervals here and having the factors over here. I just don't necessarily like that idea that much in general because it doesn't give you all the information that you could potentially get. I don't necessarily care which one of the two you do in the end. Do you understand this? Yes.
This is how we're going to need to set up some more problems if you want to show a table like that.
You will have to show a table like that.
Okay.
This problem is very simple. We're only looking at a cubic function. Let me just give you a perspective of what we're going to do from this point on. We're going to spend a lot of time graphing rational functions, root functions, trigonometric functions. They're probably going to be much more complicated than just two linear factors. And so the only way to keep track of everything is to actually write them out in an explicit form. Yes?
So f prime of x was x minus 2
Yeah, see, f prime of x is 3 times the two factors. And as I said, 3 doesn't really play a role in the sign because it's just a positive number. So the point is, x minus 2 times x plus 2 end up being equal to f prime. Well, 3 times that. Is that making sense? Yes.
Wait, so we just factored apart 3x squared minus 12, and that's what we get, and from there...
Isn't that what I did?
Huh?
Isn't that what I did?
Okay.
Is this making sense? Yes. I'm sorry, say that again? If it doesn't factor, in what sense?
Where you can't grab a couple different.
Well, let's talk about rational functions or even polynomials for that matter, right? You need to figure out where the first derivative is 0. That basically accounts to factoring out completely. The only way you can't factor it out to linear factors is if you end up with a square that can't be factorable. Now, if it's a square, it's a quadratic that can't be factorable, you can figure out if it's either positive or negative, and you incorporate that into your problem. So if you have, like, for instance, x squared plus 1 in part of your factors, that's always positive, so it won't affect in any shape or form the end result. Is that making sense? We'll play a lot more with these. That's basically, today and Friday, all we're going to do is basically learn how to graph things. So we'll see a lot of functions. So what is our conclusion? Normally, the way I like to do things is also add a column here for f, and I'm going to write it in symbols rather than words, just because it saves time. When f prime is positive, function's increasing. F prime is negative, function's decreasing. F prime is positive again, it's increasing again. So increasing intervals from minus infinity to negative 2, union 2 to plus infinity. Decreasing from minus 2 to 2. Notice that I didn't include negative 2 and 2 in these intervals. Part B asked for local min or local max. What would be the local mean? What would be the local max?
Local max is -2, local min is 2.
Is that making sense? Yeah?
Oh, wait, that's backwards.
Oh, I wrote them. I said what's local max, what's local min, but I actually had them written the other way around, so when I wrote them I just... Is this making sense? When we're going to start graphing, because by the way, right now we're only trying to get information about how a function looks like. And the next step would be to actually graph it. And we're going to take a lot of intermediate steps to graph it, like, what's the y-intercept, can you come up with the x-intercepts, and so forth. And one of the things we're gonna do, and this is why I like this particular way of drawing the table versus your textbook's way of drawing the table, is because what I'm going to do later on is, I know at minus 2 and 2, your f prime is 0, but I can actually plug in negative 2 in for f and 2 in for f, and I can write them in the table. That way I know exactly what those maximums and minimums are when I graph them. And we'll see this a little later on. Do you want to see another one, or should I talk about second derivatives? Second derivatives? Okay. So the question would be, what can I say about second derivatives? How would the second derivative help me in determining anything in relation to my function? And as it turns out, that's when we're actually going to start finding out about inflection points. So, let's see. I'll give you the definition first, then I'll draw you a graph to kind of show what we're actually talking about. If the graph of f lies above all of its tangents on an interval capital I, then f is called concave upwards on I. And on the other hand, if the graph of f lies below all of its tangents on an interval I, then f is called concave downward on I. This definition might seem a little confusing. What does it mean for all the tangents to lie below the graph? Think about if you have something like this, then all the tangents are below the graph. This is called concave up, and the way we usually write it is we just say it's CU. If your function looks like this, then all your tangents lie above it, and so we call this concave down. The way I usually like to describe things, I mean, that's actually how I was taught when I was young, is that concave up holds water. Concave down doesn't. If you don't like water, I guess you can use wine, tequila, or any other, beverage of your choice. But the point is, if it rains, water will get accumulated in a concave upward, but it will not in a concave downward. Okay? Is this making sense? Okay. As I said, the actual definition might not necessarily make a whole lot of sense, but the actual description should be very simple. Okay. Another definition says the following. A point capital P on a curve y equals f of x is called an inflection point if, I'm going to write things a little different than your textbook. Your textbook says if the curve changes from concave downwards to concave upwards, or if it changes from concave upwards to concave downwards. What I'm going to say, and you tell me if it makes sense, if f changes concavity at P. Is that making sense? Is everybody understanding that means that it goes from up to down or from down to up?
Like x cubed.
Like x cubed, yes, at 0. Is this making sense? Okay, so up to this point we haven't said anything about the second derivative. How would the second derivative actually help us? So let me write it out. Concavity test says if f double prime of x is strictly bigger than 0, for all x in I, then f is concave up in I. Part B, if f double prime of x is less than 0, for all x in I, then f is concave down in I. Why is this the case? The answer is very simple. If you come back to my lovely pictures over here, let's look at the orange first. If you look at the actual derivative, okay, look at the slope of each tangent line. Let's say here I'm looking at, I don't know, minus a half, then I'm looking at 1, then I'm looking at 2, 3, 4, or whatever. The key idea is, as x moves, your function f prime is increasing. Is everybody seeing this? Since the first derivative is increasing, second derivative has to be positive. Why? Think about the first derivative and the function. We said when the first derivative was positive, your function was increasing. So now we're just moving at the first and the second derivative. If you look at the green lines, again, well, I guess this is kind of like 0, but the point is 0, minus 1, minus 2, and so forth. Your slopes are decreasing, which means the first derivative is decreasing, which means second derivative has to be negative. Is that making sense? Okay. So, we don't have it written out. I'll just say it in a couple of words. How do you find inflection points? You look where the second derivative is equal to 0, and moreover, you look where the second derivative changes sign. Well, no, we're actually going to be interested again in the whole interval. We're going to actually test when the second derivative is positive, when the second derivative is negative in order to graph. So we're going to have that information. Similarly to minimums and maximums, we already have the information from the first derivative. We're just applying it. Okay. The last bit of theory before we look at some problems would be the second derivative test. It says the following. If f prime of c is equal to 0 and f double prime of c is bigger than 0, then f of c is a local minimum. In part B, if f prime of c is equal to 0 and f double prime of c is less than 0, then f of c is a local maximum. Is this making sense? Think about what it says. If you look at A, f prime of c is equal to 0 means c is a critical point, right? We're saying second derivative is positive, which means my function is concave up. So if it's concave up and the derivative is 0, it has to have a minimum, right? It's where the water gathers, or I guess tequila. And if you look at B, second derivative is negative, so you're looking at concave down, and so you'll end up with a maximum. Is that making sense? Okay. So, returning to our function, to our problem 1 on page 217, f of x was equal to x cubed minus 12x plus 1. F prime of x was equal to 3x squared minus 12. And part C of the problem asks to find intervals of concavity and inflection points. So we look at f double prime of x, and f double prime is 6x, right? F double prime of x is equal to 0, means x is equal to 0. So if I want to draw a table, my second derivative is negative up to 0 and positive from 0 on, which means f of x, and this is going to be this is going to be the way we actually I'm going to write things. It's concave down, concave up. So smiley face or sad face. That's another way of thinking about things. Right? You're happy, it's positive. You're sad, it's negative. Well, you like mnemonic things, right? Sokatoa, foil, and all the other things, so you know. The butterfly effect.
That's exclusive.
Is this making sense? Okay. Let's see. Problem number 17. We're going to have a couple of things to look at. The first type of problem that we're going to look at is we're given a bunch of conditions, and based on those conditions, we need to come up with a graph of a function. Okay? So the conditions are the following. F prime of 0 is equal to f prime of 2 is equal to f prime of 4 is equal to 0. F prime of x is bigger than 0 if I was looking at 18. If x is less than 0 or x is between 2 and 4. F prime of x is less than 0 if 0 is less than x is less than 2 or x is bigger than 4. F double prime of x is bigger than 0 if 1 is less than x is less than 3. F double prime of x is less than 0 if x is less than 1 or x is bigger than 3. Wonderful. By the way, the reason why we're kind of doing these problems is kind of two-folded. First of all, we need to identify how do we actually use the derivatives and everything else in our graphs. And later on, what we're going to do is we're going to actually be given a function, and we're pretty much going to have to come up with this stuff. Okay? Now, the idea is I have this stuff. How can I use it to graph it? So, as the first thing that I would ask for you, or I would ask would be, do we have any local mins? Do we have any local maxes? And do we have any inflection points? And here, I'll write it above here. F prime of 0 is equal to f prime of 2 is equal to f prime of 4 was equal to 0. So the first thing we should notice is, can you tell me what the domain of f would be? While reals.
I'm trying to imagine it kind of being like this.
Why are you trying to imagine it that way?
Because when I look at the top one, I see that those 3 points are x intercepts, right?
No.
No.
They're derivatives, not function. Notice there's absolutely no mentioning of anything about relating to f of x. Everything in terms of f prime and f double prime. However, if you look at the second and the third line, it says f prime of x is bigger than 0 for all x's that are negative and x's that are between 2 and 4. F prime of x is less than 0 for all x's between 0 and 2, and x is bigger than 4. That means that f prime of x is defined everywhere. Is everybody understanding this? Since f prime of x is defined everywhere, clearly f is defined everywhere. So we're looking at the entire real line. Do you understand this? Okay. Local mins. I'm waiting. What does the first derivative test say? C has to be a critical point, right? How many critical points do we have? 3. 0, 2, and 4. Right? Is 0 a local min or a local max? Or neither? F prime is bigger than 0 when x is negative. It's less than 0 when x is between 0 and 2. Right? Which means for first derivative changes sign at 0 from positive to negative. What does that tell us? Max?
Oh, wait, what just happened? What did you say?
I don't know. What did I say?
It said something about something 0.
At 0, the first derivative changes from positive to negative.
Alright, so we're looking at the second one?
Yes, second and third.
Okay.
What happens at 2? Negative to positive, which makes it a minimum. And at 4? Bless you. It changes from positive to negative, so it becomes maximum again. Right? Would you like the arrows better? Maybe that would be better, because you seem to be kind of confused. So let's take an aside and think about what we're actually talking about. I have... Maybe this will shed a little more light on the subject. I have 0, 2, and 4. My first derivative is 0 at all these points. Now, what do I know from my information? F prime is positive before 0 and between 2 and 4. And it's negative between 0 and 2 and when it's bigger than 4. Right? Which means my function is increasing, decreasing, increasing, decreasing. Is this better to recognize where a function has minimums and maximums? Yeah? Okay, how about inflection points? So how about we actually do another graph, since this seems to work better, or I shouldn't say graph, but table, that relates f double prime. So what do I know? The issues that I'm looking at are 1 and 3, right? We're assuming it's not given, but we're assuming the second derivative is nice enough that it actually is 0 there. So, what do we know? It's positive between 1 and 3 and negative outside. Right? What else do we know? That basically tells us that your function's sad between minus infinity and 0 and 1. Happy between 1 and 3, and sad from 3 on. Right? Yes?
How to know when the second derivative is 1 and 0?
What?
See in the row,
Uh-huh.
second derivative that.
Uh-huh.
You see where 1 is,
Uh-huh.
and 0. How do we know that?
So what you're saying is that f of 1 is equal to f double prime of 1 is equal to 0, not f double prime of 0 is equal to 1.
Okay, yeah.
As I said, I don't necessarily know this is 0. I'm just going to assume that it's nice enough that it is 0. I don't necessarily care if it's 0 or not.
It doesn't matter.
All I know is inflection points happen when the concavity changes. So my concavity changes here, and it changes here. As a ground rule, that's where the inflection points are going to be, where the second derivative is 0. However, there are instances in which the second derivative doesn't exist, and you still end up with an inflection point. Actually, there's a point in which the first derivative doesn't exist, and you still have an inflection point. If you don't believe me, I'll show you an example in a second. Okay, so this is an inflection point. This is an inflection point. What are we looking for as far as the graph is concerned? I have 0, 1, 2, 3, and 4. Right? Let's see. 2 is a minimum, 0 and 4 are maximums. So let's say I'm somewhere over here for a minimum, and let's say I'm up there for maximums. Right? What else do I know? I know my function's concave down from minus infinity. So my function's concave down from minus infinity up to 1. I have a maximum at 0. So that would be one way of drawing it. Is that making sense? Between 1 and 3, my function's concave up, and at 2 I have a minimum. So and then from 3 on is again concave down, and I have a maximum. Is this making sense? Everybody sees this?
Well, so the first table we made had to do with finding our points. The second table we made had to do
We're always going to do two tables. In all of these problems, whenever we're going to start talking about, and we're building our way to actually get to the next section, which is just graphing in general. We're always going to do two tables. One table involving the first derivative, second table involving the second derivative. First derivative tells us minimums and maximums, and increasing, decreasing intervals. Second table, second derivative tells us concavities, and it tells us inflection points. Okay? Is this making sense? Okay. Should we do another one? Like this? Okay, 19. We have f prime of x is bigger than 0 if the absolute value of x is less than 2. F prime of x is less than 0 if the absolute value of x is bigger than 2. F prime of negative 2 is equal to 0. The limit as x goes to 2 of the absolute value of f prime of x is infinity. and f double prime of x is bigger than 0 if x is not equal to 2. Okay? Don't get scared. Absolute values actually are just a way of writing less stuff. That's all there is to it. First row gives us a lot of information. What's the information? It tells us that between -2 and 2, your first derivative is positive. It tells us outside of them, our first derivative is negative. Is everybody seeing this? Now, if you read the second line, it says f prime of -2 is equal to 0. So I put the 0 here. It also says the limit as x goes to 2 of f prime is infinity. That tells me that that's a vertical bar. It basically tells me that my first derivative has an infinite slope technically. It just tells me that my function is not defined there. My first derivative is not defined there. Okay? So what do I know about my function then? It'll be decreasing, increasing, decreasing. Right? What else do I know? I know this is a minimum. Do I know that the other one is a maximum? It is not a maximum. Why is it not a maximum? I have a vertical slope, right? So how would I be able to get a maximum if I have a vertical slope? I wouldn't be able to. Is that making sense? Okay. What else do I know? Second derivative is positive everywhere except at 2, right? Which basically means your function is concave up at all times, right? So how would the graph look like? If I assume 2 is a vertical asymptote, which I don't have to assume, okay? But it just makes life simpler if you do assume that. And I have at -2 as a minimum, so I'm somewhere over there. My function is concave up at all times. So that's a graph. Is this making sense? Okay, let me just say one thing. This problem says find a particular graph. They don't have to be the same at all times. I could easily have a graph that looks like this. With a maximum at 2, but a cusp at 2, which means my first derivative doesn't exist, yet my function actually does exist. I will still maintain the concavity throughout, and I would still satisfy all my conditions. Is everybody understanding this? Okay. So we'll stop here, obviously.